very good morning. Am I audible?
Yes, sir.
Okay. Let me share the screen. Yeah, screen is visible.
Yes.
Okay. Yes. So, so we have left with the Green's theorem and what it gives you physically, okay, or uh, what kind of application it has. To explain them, I need to define two very important concept in vector calculus, known as divergence of a vector field and curl. Okay, curl of a vector field. And so, before going to learn this statement of the Green's theorem, because the statement will say that line integral is converted into the double integral. Okay, under some mathematical assumptions. Okay, so if you have this form, you have the right side, the integrand will have this form, and so it is a part of memorizing, but the thing is how it is help you in solving the real life applications. So to understand that, let's define two entities in vector calculus, rather important entities. So let's first uh, introduce this divergence of a vector field. So this vector field, you can understand it may represent the velocity vector of a fluid flow and okay, a gradient field and so on. Okay, so sometimes it also divergence also interpreted as by physicists and engineers by flux density. Flux density of the vector field of a vector at a point x comma y, you can say. So to understand that, let's look at the very simple geometry. Okay, so let's have this is a region R, and you want to interpret the divergence at point x comma y, or velocity field at point x comma y, divergence of a velocity field at point x comma y. So a very simple geometry, what we have understood is the rectangle. So you may draw a rectangle which will be entirely lies inside the region R. Okay, so this is the point x comma y. Okay, and as this is the point, uh, this is in the direction of x, it is with delta x here, and this is some delta y. So this can be now identified as x plus delta x comma y. Okay, this can be identified as x plus delta x comma y plus delta y, and this point is can be identified as x comma y plus delta. Okay, so these are 4 points are identified. So these as delta x and delta y tends to 0. Okay, that will actually give you the flux density of a vector field at point x comma y inside the now. So how to identify the rate at which a fluid leaves the rectangle uh, across? So there are four edges, okay. So which we can name as let's say this is, you can name as bottom edge of length delta x. Okay, this is the top edge. This is, you can say, left edge. This one is right edge. So the rate at which fluid leaves the rectangle across the bottom edge, what it will be. So you have to look in the outward normal to this edge. The outward normal to this edge is nothing but, so outward normal means outside. Okay, so outward normal means you are having in this uh, outward normal in the direction of y, but in the negative direction of y. So the rate, and it is having the length is delta x. So what will be the, so I'm just going to tell you that the rate at which fluid leaves the rectangle across the bottom edge is approximately is going to be the velocity field or vector field at point x comma y dot, see the bottom as you are having, you are looking at the nearer x comma y, because as delta x and delta y tends to 0. Okay, so velocity field at x comma y dot product with unit outward normal with multiplication with the length of that bottom as is delta x. Now, if you recall, I'm just going to recall here that that velocity field is f of x comma y is equals to plus m of x comma y I plus n of x comma y j. Okay, so once you have this I component and j component, so you know how to perform the this dot product. So this is going to be minus m, not n, n j component, right? So n of at x comma y time delta x. So similarly, I say the top s. So exit rates, I can say, okay, uh, across the top S. Okay, so in the top S, you have the outward normal in the direction of yj component. Okay, so that's going to be the velocity field at x comma y plus delta y dot product with j cap and length with the delta x, and that is going to be n of x comma y plus delta y delta x. So the total rate, I mean, the total fluid leaves, okay, the rate at which the total fluid leaves across the bottom edge and top edge will be the sum of these. Okay, and okay, right? Yes. So so from here, what we can say is so across the bottom edge plus the top edge. what it will be approximately is you have first one was minus n of x comma y delta x. The second one was a plus n of x comma y plus delta y delta x. And now this delta x is common, and you have n of x comma y plus delta y minus n of x comma y delta x. And if you assume that the component has a first order partial derivatives continuous, so that can further approximated by, because you have the increment in the direction of y, so it can be approximated by dou n by dou y times delta y delta x. Okay. Similarly, in the left as and the right as. Okay. Similarly, for the left as, okay, the left as is the side, so you have the negative direction of outward normal in the negative direction of x. Okay, so you have at field f of x comma y is dot minus I cap, and the length of that that as is delta y. So that's going to be minus mx comma y delta y. And similarly, right as is, if you let's write as here, so velocity field at x plus delta x comma y time dot product with I cap time delta y. F of x comma y dot I cap time delta y, not f of x, because it's going to be f of x plus delta x comma y dot I cap time delta y, that is equals to m of x plus delta x comma y delta y. Now, similarly as discussed above, so across the left as plus right as can be approximately now. So if you sum up these two, it's going to be dou m by dou x times delta x delta y. Now, so therefore total means from every as, so across the rectangle, so across the rectangle, what you will have is dou m by dou y plus no, dou m by dou x plus dou m by dou y time delta x delta y. This is approximately. Now, if you establish that it is across the rectangle, then you have this. Okay, and if you are interested in per unit length, okay, so then you have, so I just write that now total flux per unit area of flux density for the rectangle will be equals to that flux across the rectangle boundaries divided by the area of the rectangle. And you know, area of the rectangle is nothing but delta x into delta y. Okay, so writing here this flux across the rectangle boundary divided by the area of the rectangle. Area of the rectangle, and which is approximately is equals to dou m by dou x plus dou n by dou y Okay. Now, as delta x comma delta is already mentioned, so whenever this see, if you assume that later on what you will do that for in the continuum case, you will apply the delta x and delta y limits tends to 0. Okay, that will define the flux density of this because everything will be shrink to this point. Okay, so that will give you the flux density of the velocity field at point x comma y. Okay, so this is the interpretation of divergence of a vector field across a rectangle, you can say, or at a point x comma y. Okay, so here, so the definition is now very clear now. So I just write down definition. Okay, the divergence of a vector field f is equals to mi plus nj. It is understood that f is a function of x comma y, m and n also components are also function of x comma y. At the point x comma y is defined as divergence of f that is equals to dou m by dou x plus dou n by dou y. Now, see, I am going to introduce an operator which maybe you are already aware about. Okay, so I think that let me. So divergence of a vector field f is equals to dou m by dou x plus dou n by dou. So if you introduce the following operator, I'm just going to introduce a operator. This del is equals to I cap dou by dou x plus j cap dou by dou y. This is an operator. So I component is differentiate partially with respect to x. J component is differentiate partially with respect to y. Miss miss which is miss it is going to be operated in that way. Okay. So I can write that divergence of f as this dot product with f. Okay. So the dot product in the sense that that's dou by dou x, right? You know how to perform the dot product m plus dou by dou y n. Not that earlier dot products, you know that a dot b is equals to b dot a. Okay, but here it is not the case that del dot f is equals to f dot del. Okay, so this is an operator. These were the vectors. Vector operator here. These are constant vectors. Okay, so this way also the dot product will also give the divergence if you introduce in this. So you can increase one more dimension here plus k cap dou by dou z. You can go for divergence of a vector field in the space. Okay, you can also define that. Okay, now let's have a particular case of curl. Okay, like in the plane or okay, or you can say suppose you want to measure how a pedal wheels at a point in a fluid flying in a plane region. Okay, means you have a fluid flow. Okay, across a channel. Okay, and there is some wheel is there. Okay, and you have some plates here. Okay. So when fluid is flowing and it is fixed here, so it's but it is rounding. Okay. So how much circulation? How will you obtain the circulation density of a vector field there? Okay. So if you are interested in that, or you can say this is a spin. Okay. And around an axis. So what is an axis here? So at the center, you can see is you take a unit normal to this. So if you're talking about a planar region, let's say x comma y. Okay, in the xy plane, it is a rounding. So that the spin around an axis is z axis. Okay, that. Okay. So and when you talk about the spin around z axis, means you are talking about the k component of curl. And we will define the definition of curl maybe little later for the three-dimensional one. Okay, right. So again, to understand this circulation density, okay, we can again look at the similar fashion. Okay, means you can take a smaller at a point x comma y, you want to look at the circulation density. Again, you can draw a rectangle. Okay, and you are trying to find out the circulation along the bottom edge, left edge, right edge, and top edges. Okay, so again this length is delta x, this is delta y. Okay, now I'm just writing the directly now in rather going for further discussion. Okay, this is a rectangle around the point x comma y. Now again, as delta x and delta y tends to 0, you are able to get a circulation about the point at the point x comma y of a vector field. So let's talk about this. Let's take bottom edge. So at the bottom edge, what will be the circulation, the rate of flow is going to be the velocity field at x comma y, and it is moving in the direction of this. Okay, means I direction. Okay, right? So I dot product with I cap with length is delta x. So that's going to be m of x comma y delta x. Now for top edge, what you can have is this is the top edge. And so velocity field at x comma y plus delta y. So it's a negative direction minus I cap delta x. That is going to be with a negative sign m of x comma y plus delta y and delta x. Similarly, you can talk about the left edge and right edge. So the rate of flow along the left edge the velocity field at x comma y. So this is left edge and it is in the direction negative direction of y. Okay, it is and with the length delta y. So minus j cap delta y, that is going to be minus n of x comma y delta y. And similarly, the rate of flow along the right edge is the velocity field at x plus delta x comma y and in the direction of I, the positive direction is dot j cap with length is delta y is going to be minus n of x plus delta x comma y delta y. Now again, if you are going to look at the top edge plus bottom S top S plus bottom S is approximately, so you can look at here, so m of x comma y minus m of x comma y plus delta y times delta x. Okay, so that's going to be m of x comma y minus f of x, m of x comma y plus delta y time delta x. Now this is going to be further can be approximated by minus dou m by dou y delta y delta x. Again here we assume that that the component has continuous first order partial derivative. Similarly, if you sum up left edge and right edge, what you will have is this here plus, right? Because j component is plus. So if you go with the left s plus right s, similarly is approximately you have n of x plus delta x comma y minus n of x comma y delta y, right? Yes. So and that can be further approximated by dou n by dou x delta x delta y. So again, you can talk about now per unit length. Okay, so that's going to be now I'm defining circulation. So total circulation around rectangle divided by area of rectangle is equals to approximately, if you sum up, you are going to be dou n by dou x minus dou m by dou y. And if you limit apply delta x and delta y tends to 0, that will define the circulation density of f at x comma y. Now later on what you will see, this is going to be the k component of vector field, of curl of f. Okay, you will see that this is nothing but the k component of the curl of the vector field f. Okay, so means somehow suppose this curl of f I define, and the k component can be obtained by taking the dot product with k, can be given by dou n by dou x minus dou n by dou y. So it is this when you have spin around an axis, that is a z axis. Okay, similarly for means if you go for or if you go for x axis or y axis, similarly you can discuss about it. Now you have both the physical interpretation of both the integral term, okay, in the Green's theorem. Okay? So let's come back to the Green's theorem. So the first integral. Okay, so let's first read the statement here. So let C be a positively oriented, simple, closed, piecewise smooth curve in the plane. So what we understood by this positively oriented means anti-clockwise. Okay. Simple closed means there is no self intersection of the curve, means this is not allowed. Okay. There's no self intersection, not touching also. Okay. That's also not allowed. Simple closed curve. Positively oriented means anti-clockwise direction. Okay. So that is. Now piecewise smooth means it is not necessary that entire curve is smooth. Okay. Maybe piecewise smooth means, I hope you can understand by meaning of piecewise continuity. Okay, means you have the only finitely many points where the you have you don't have smoothness. For example, you have a rectangle. Okay, so rectangle across, this is a C1, C2, right? This is a C curve, but it's a piecewise smooth. So C1, C2, C3, C4. It's a positively oriented, simple, closed, and piecewise smooth because you have the sharp edges at these points where you will lose the smoothness. But they are finitely many. Okay, so such type of smoothness is known as piecewise smooth. If you have finitely many points where the curve is not smooth. Okay, right. Or you can subdivide the curve into finitely many smooth curves. Okay, that's also another way to look at the piecewise smoothness. Now, let D be the region bounded by C. So D is the region bounded by C. So enclosed by C. Okay. Now, if M and N have continuous partial derivative on an open region containing D. So if you have the information that this capital M and capital N have continuous partial derivatives, first order partial derivatives on an open region containing D. Means it is not necessary that M and N should have the continuous partial derivative on the boundary. It is necessary to have only inside the open region. Okay, then you have the following. Now, I am going to write in vector form also. Let me show you that what is m dx plus n dy is going to be mi plus nj dot product with dx I cap plus dy j. So in other words, that is going to be f dot dr, or you have this is tds. So tangential vector, tangent vector. So what it will give you? So if you are acting, means kind of work done, or you can have the circulation density. Okay, so you have this is the curve. So here is the simple closed curve C. Okay, at any point, so it is f dot t. You are moving in the direction of. So you take at any point, you have in the direction of acting, that force is acting in the direction of this. Okay, so it will move along this. Similarly, like this here, you can draw the tangents. Okay, so it will give you the circulation density at the point. Okay, so the first integral represent the circulation density. Okay, so this first integral will represent the circulation density. Okay, and what is the vector form of this is integration Cf dot T ds. Okay, so this will give you the circulation density. Say one form. Across the region D. Okay, now second integral. If you look at the second integral, so what is this? So that's the very first thing. Okay, another thing is another integrand is what? M dy minus n dx in the line integral. What it is in the notations? This is mi plus nj dot product with dyi minus dxj. Now, if you look at this, this is as it is, it's fine. This is fine. What is this? This is nothing but is going to be dyi minus dxj cap. It is very well to verify, very easy to verify. That's going to be perpendicular to dxi plus dyj. Means tangential vector. Means it's going to denote a normal. Okay, so this is going to be unit normal. We are not mentioning here. Okay, it may be or it may not be NDS. So this is the normal. So because this is perpendicular to the tangential vector, it's going to be normal. Means outward flux. So you have here in the if you C, and if you have the tangent E, and you have the out. So this is going to be N at any point. Okay, so it will give you the, so you have the outward flux across the boundaries. Okay, so if you want to obtain outward flux density, you can use this, and this vector form of this is integral C F dot NDS. Okay, so the first form will give you the circulation density, can be used for circulation density. The second form can be used for the finding the outward flux. And the right hand side will see in the right hand side. So now if you more carefully, now I can also write this now. What I can write in finally is the Green's theorem. Green's theorem gives you integral C F dot TDS circulation density. Okay, that's going to be double integral over D. The D is the reason enclosed by C. That's going to be the curl of F dot K component dA in the vector form. Okay, circulation density, because why unit outward normal is K is because we are talking in the plane region. Plane region is XY plane. Okay, so the unit normal to the XY plane is what is the Z1. Okay, and the Z has the component K. That's why here is K component. Okay, and that is going to be double integral D dou N by this is going to be dou N by dou X minus dou M by dou Y, right? Yes. Dou N by dou X minus dou M by dou dx dy. Okay, that's a first vector form. Another vector form for finding the outward flux is F dot N ds. That is going to be double integral over D divergence of F dx dy. You know what is divergence of F is nothing but double integral D dou M by dou X plus dou M by dou dx dy. So sometimes it is also known as tangential form, and that's normal form. Okay, of the Green's theorem. Right. Now let's verify the Green's theorem with one example. So let's take this example 1. So verify Green's theorem for the vector field F is equals to. So vector field F is given to be x minus yi plus xj, where C is the unit circle oriented positively. C is the unit circle. So I can write parameterization of that is cos t I plus sine t j, where t 0 less than equals to t less than equals to 2. Okay. So this is C positively oriented. This is the reason D means D is nothing but the disk, open disk, centered at origin with radius 1. Now the Green's theorem tells you integral CF dot TDS, that is you have CF dx plus n dy is equals to double integral over d dou n by dou x minus dou m by dou y dx dy. So this is what the tangential form, and which is easy to memorize as well. So dy coefficient will be differentiated partially with respect to x minus dx coefficient partially with respect to y. Okay. Now, similarly, you can discuss for the this normal form as well. So let us have this is what is m given. F is equals to x minus y I plus xj. So this implies m equals to x minus y and n equals to x. So this implies dou n by dou x is 1 and dou m by dou y is minus 1. Okay, so I will call this as 1. Now, right hand side of 1 equals to double integral over d. D is nothing but x square plus y square strictly less than 1. Okay, and that is dou n by dou x minus dou m by dou y. So this is 1 minus 1 dx dy. So that is going to be 2 times double integral of x square plus y square less than 1 dx dy, and this is nothing but the area of the unit circle, that is unit circle centered at origin, that is going to be pi. So the value of this integral is 2 pi. So if you are able to observe that, you can write down directly. Okay, or else you can use the parametric forms. Okay, or polar coordinates, whatever. Now we have to evaluate left hand side now. Now left hand side of 1 is equals to integration cm dx plus n dy. We already have the C parameterization. Okay, cos t I plus sin t j, 0 less than equals to t less than equals to 2 pi. Okay, so what is dx is minus sin t and dy is cos t. Okay, and m is x minus y. So this is 0 to 2 pi x minus y. So cos t minus sin t type dx is minus sin t plus n is x. Okay, x is cos t times dy is cos t dt. So cos dt is missing here. Now this is equals to integration 0 to 2 pi. Now this is going to be minus cos t sin t So this is sin square t plus cos square t, right? Cos square t plus sin square t, that is 1 dt. Now, what is equals to? This is equals to integration 0 to 2 pi 1 minus cos t sin t dt. The first term integration will give you 2 pi minus integration 0 to 2 pi 1 by 2 divided multiply 2 sin t cos t dt. And so this is equals to 2 pi minus 1 by 2 integration 0 to 2 pi 2 sin a cos a sin 2a sin 2 t dt. And now if you integrate, what you will get is upper limit minus lower, because sine is a periodic function over the interval 0 to 2 pi. Okay. Or you can do one more step here and you can prove that this value of the integral is 0. So that is equals to 2. This verifies the Green's theorem. Okay. So then similarly, normal form also you can verify. Okay. That will give you the verification of the Green's theorem. Now, let's see another example. So another example is you have to evaluate the following integral where C is the square cut from the first quadrant by the lines x equals to 1 and y equals to 1 with positive orientation. So here also we can verify Green's theorem. Okay. Xy dy plus y square dx. Xy dy plus y square dx. Xy dy plus y square dx. And what is C is the curve cut from x equals to 1 and y equals to 1. This is square cut. Okay. Positively oriented. This is, let's take O, A, B, and C. Okay. Now, Green's theorem. So for the Green's theorem, you need to verify that C is a positively oriented, piecewise smooth and simple closed curve. Okay. So everything is here. Okay. Is a positively oriented. It's a piecewise smooth. Okay. Sharp except finitely many sharp edges. Everything is fine. And it's a simple closed curve. There is no self-intersection and touch of the curves. Okay, in between. So every condition is verified. Now, so Green's theorem implies integral C. See, it is written in dy first and dx second. Okay, I will write first dx and then dy. So y square dx plus x time y dy is equals to double integral over d dou by dou x of dy component, that is x into y, minus dou by dou y of dx component, that is y square dA or dx dy. Now this is equals to double integral over d dou by dou x is y minus this is 2y dx dy. So that's equals to minus double integral over d by dx dy. Now this is square cut. What are the limit of x and y? Minus 0 to 1, 0 to 1, First, so Fubini's theorem allows you whichever way first, okay, because of the constant limits. So that's going to be minus. So if you integrate first with respect to x, y is a constant, y is treated as a constant. Integration is x, upper limit minus lower limit will contribute 1. Okay, integration 0 to 1 by dy, and that is equals to further y square by 2, so it's going to be minus 1 by. Now, if you want to verify the Green's theorem, what you can do is for verification of Green's theorem, you can evaluate, right, integral c y square dx plus x into y dy is equals to integration along OA plus AB plus BC plus C. So you have to use the parameterization of the curve along each line. Okay. Now, along OA, y is equals to 0, right? Along OA, if you recall here, along OA, y equals to 0. And x is running from 0 to 1. Okay. So, x equals to t, y equals to 0, 0 less than equals to t less than equals to 1. So, integration OA is 0 to 1, OA y square dx plus x times y dy is equals to integration 0 to 1. Y is 0, here is also 0, so nothing is there, so that's 0. Now, similarly, along AB, what is that? Is along AB is x equals to 1 and y equals to t at t lies between 0 to 1. Okay, so along AB, x equals to 1, y equals to t, 0 less than equals to t less than equals to 1. So dx is 0 and dy is dt. So what you have integration along AB, y square dx plus x times y dy is equals to integration 0 to 1. Now dx is 0, so first term will vanish. Another is t times dt. Okay, x is 1, y is t, dt, so it's going to be t square by 2, so it's going to be 1 by 2. Now, along BC, if you recall, y is equals to 1 and x equals to t and t. So you are oriented in positive direction. So t is equals to 1 to t equals to 0. Okay. So integration along BC, this is y square dx plus x times y dy. So that's equals to integration 1 to 0. Now y square is 1, dx is dt, dy is 0. So this is going to be minus 1. Now along CO, x is equals to 0, y equals to t, and t is equals to 1 to t equals to 0. Right? So this is along CO, y square dx plus x times y dy. Now dx is 0. Okay. And x is 0, so second term will also does not contribute anything, the value is 0. Okay. So therefore, this all implies integral along C, y square dx plus x times y dy is equals to 0. Along OA is 0. Along AB is 1 by 2. So I hope you got it that the final value is minus 1 by 2, and it also verifies the Green's theorem. Right? So this is 0, have 1 by 2 minus 1 plus 0. And that is going to be minus 1 by 2, and which is just now obtained that minus 1. Now, let's look at the following problem number 3. Evaluate the integral where C is the triangle with vertices at so and so. Okay, so example number 3, it is, so you are supposed to evaluate x to the power 4 dx plus x into y dy. Yes, where C is the triangle with vertices 0, 0, 1, 0, 0, 1, 2, 0, 0. So 0, 0, 1, 0, 0, 1. And D is this region enclosed by this. And now, you know, this is the line x plus y equals to 1. Now, since this is a positively oriented of 0, 0 to 1, 0 to 0, 1 to 0, 0. So positively oriented, piecewise smooth, simple closed curve. So the Green's theorem is applicable. Okay. And D is the region enclosed by this triangle. Okay. So the Green's theorem implies, so Green's theorem implies that is equals to double integral over D. So dy component partial derivative with respect to x, that is x into y, minus dx component partial derivative with respect to y, that is x to the power 4, dx dy. Now this is equals to double integral. So this is, I will say line integral equals to, okay, so double integral over d. So dou by dou x is y of this, and this is 0, y dx dy. Now the limit of d, now you can find out. Okay, it's a triangle. Okay, so this is x plus y equals to 1. X is running from 0 to 1. Y is running from 0 to 1 minus x. Okay, it's very simple to obtain the limits. So that is equals to, this implies line integral is equals to x is 0 to 1, y is 0 to 1 minus x, y dy dx. Now this is equals to integration 0 to 1. Now y square by 2, 0 to 1 minus x dx. So lower limit will not contribute anything. So you have 1 by 2, 1 minus x whole square. So you have 1 plus x square minus 2x dx. Now you can integrate further. So it will be equals to 1 by 2. The first term, x plus x cubed minus x square, minus x square, upper limit and lower limits. So that's going to be 1 by 2. So lower limit will not contribute anything. Upper limit 1 plus 1 by 3 minus 1. So that's going to be 1 by 2 into 1 by 3. That's going to be 1 by 6. Okay, so this is the example 3. Now, for example 4, evaluate the following line integral where C is the boundary of the semi-annular region between the semicircles x square plus y square equals to 1 and x square plus y square equals to 4. Example 4, you want to find out this line integral y square dx plus x into y dy. And what is C is the annular region x square plus y square equals to 1 to x square plus y square equals to 4. Okay, and again another reason, so we are assuming that, see, to apply the Green's theorem, what you require it is going to be positively oriented. Okay, this is the curve. Okay, and this is the region D. Now, since again this is a simple closed curve, piecewise smooth, because you have the sun as is here. Okay, and positively oriented, so it verifies the assumptions of the Green's theorem. Now Green's theorem gives you that is equals to, now double integral d, we have just now solved, this is going to be dou by dou x of dy component, that is x into y, minus dou by dou y of dx coefficient, that's going to be y square dx dy. So this is equals to, will be that will give you I equals to double integral over d minus y dx dy. Now, since it's an annular region, there are various ways to look at it. One is you have square root of 1 minus x, y limit is square root of 1 minus x square to square root of 4 minus x square. And x limit is from 1 to 2. Another way is you can also look at in the polar form. Okay, so you know polar forms, so that will give you r limit is 1 less than equals to r less than equals to 2. Okay, and 1 less, and theta limit is 0 less than equals to theta less than equals to pi. What is x? X equals to r cos theta, y equals to r sin theta, and then dx dy will be changed into r dr d theta. Okay, so there are various ways to solve this integral now. Okay, you can verify by any one of this. I will do for this, you can verify by other one. Okay, so therefore I is equals to minus integration y is r sin theta, dx dy is r dr d theta, r limit is 1 to 2, theta limit is 0 to pi. So this is equals to minus integration 0 to pi integration 1 to 2 r square sin theta dr d theta. Now you know when you integrate with respect to r, sin theta is a constant, so r cube. So 1 by 3 integration 0 to pi r cube 1 to 2 sin theta d theta. Now, so 2 cube is 8, 8 minus 1 is 7, so it's going to be minus 7 by 3 equals to minus 7 by 3 integration 0 to pi sin theta d theta. Now sine theta integration is minus cos theta minus cos theta 0 to pi. So minus minus plus here. Now 7 by 3. Now cos pi minus cos 0. So minus 1 minus 1 minus 2. So it's going to be minus 14 by 3. The value of this integral is minus 14 by 3. Okay, right. So these are the problems for Green's theorem. Okay. Now let's so one note you can have is it can be one another way to identify the area, okay, of the region bounded by the curve C. Means, see, you have seen the finding the area in terms of double integral, right? Now here you will get an idea how to find the area of the curve bounded by the curve using the line integral. Okay, so if you look at the Green's theorem, okay, if you look at the Green's theorem, so what Green's theorem tells you is you have integration C m dx plus n dy is equals to double integral d dou n by dou x minus dou m by dou y dx dy or dA. Now, if you have dou n by dou x minus dou m by dou y is equals to 1, what it will give you? The area under the curve, area of the region D. Okay, so if dou n by dou x minus dou m by dou y is equals to 1, then this is have 1, then integral C m dx plus n dy gives the area of the region enclosed by C. So can you give an example of such one is if I take n equals to x by 2 and m equals to minus y by 2. Okay, I'm taking so example. So here it can be multiple examples. So n equals to x by 2 and y equals to, oh sorry, not y, m equals to minus y by 2. So this implies m dx plus n dy is equals to 1 by 2 times x dy minus y dx. Also, dou n by dou x minus dou m by dou y is equals to 1. 1 by 2 minus 1 by 2, that is 1 by 2 plus 1 by 2, that is 1. So, therefore, this implies, so area of the region enclosed by C is equals to 1 by 2 C x dy minus y. So here it is C is where C is positively oriented, piecewise smooth, and simple closed curve. Okay, so another way, so for with the line integral also you can look at the area of the region. Okay, right. So this is what regarding the Green's theorem. Okay, now let's define the important entities in the 3-dimension, that curl and divergence of a vector field, and then we will end. Okay, so curl of a vector field, so let F be a vector field, and which is, I don't think so, it is not need to be repeat that M and N and P are the functions of X, Y, and Z, be a vector field, and suppose the first partial derivatives of the component functions exist. It is required, why? Because in the definition. So define the curl of a vector field F as follows. So first, so it is very easy to memorize. It's a determinant of the following. The first row is I, J, K, means X direction, Y direction, Z direction. Second component is also, second row is also fixed. Okay, first row is fixed, second row is fixed. Okay, second row is below I you have partial derivative with respect to X. Below J, that means Y direction, you have partial derivative with respect to Y. With Z direction, you have a partial derivative with respect to Z. So these two rows remain fixed. Okay, and the third row will be obtained by the given vector field. So the first value is the I component, second value is the J component, and third value is the K component. Okay, and you know how to evaluate this determinant. That I don't think so it is need to be repeated. Okay, what I can make here comment is you can find out the K component. K component is users, right? So dou n by dou x minus dou n by dou y. What we just learned in the circulation density case. Okay, so this is how this curl of a vector field is defined. Okay, and it is already mentioned that curl F measures how quickly a tiny paddle in some fluid in a vector fluid moves around itself. It will give you a spin, okay, around an axis. Okay, so if the curl F0, it will represent that there is no rotation. Okay, and if it is non-zero, there is some rotation. If there is no rotation, means irrotational field. Okay, and you have the divergence. I have already discussed the divergence in the plane region. Now in the space, you can extend it for this velocity vector field, for vector field F. The first partial derivative of the component functions exists. We define the divergence of vector field F, this dot product. I have already given you that introduction of this operator. Okay, that is going to be I component is dou by dou x, Y component is dou by dou y, and Z component is dou by dou z. Dot product with F. Not that you cannot write del dot F as F dot del. That is you have to keep in mind. Okay. So again, if divergence is this entity is a negative number, means you are having compression. If it is a positive number, means you have an expansion. Okay, you will see an expansion in the fluid or gas. Okay, and if there is nothing, either neither positive nor negative, means zero, then we say that the fluid is incompressible. Okay, right. So we can leave now. Thank you. If you have any doubt, you can ask. Okay, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.